have your minor loss, which is your K. That will be the velocity squared 2g. Okay, so 2 times the divided by the 2 times the gravity. Now solving for the Reynolds number at the 200 mm pipe. So at this part, okay, so we have a total length of that is 10 meters. So assuming they will be using to maximize yung length na lang nito. So starting from here going there, we are going to assume it is already a 200 length of pipe, so excluding at this point. We have the equation for our Reynolds number, so that will be your RE. So this is equal to the density of the water, then multiply it by the density of the pipe times the diameter of the inside pipe, then it is divided by the absolute dynamic viscosity. So for the properties of the density of the water, so we'll go to the table. Okay, now referring to this, we're going to attach now table. Okay, so we have the given temperature, so we have the given temperature which is 20 degrees. So I'm gonna highlight this 20 degrees. Okay, so anyway, so that is 20 degrees. Density of the water at 20 degrees. So the density of the water is 998. Okay, and for the velocity, we do not know the velocity. The inside diameter is also given, that is about we'll use the 0.2, then 1.0 times 10 to the power of -3. Now for let's solve the volume flow rate. The velocity. So we have the equation, your volume flow rate is equal to area times your velocity. So your velocity is equal now to Q, or volume flow rate divided by your area. Q, we have pi over 4 times the diameter. So this is equal to, so volume flow rate, looking at the problem, we have 0.06 cubic meter per second. So 0.06, so this is cubic meter per second divided by pi over 4. Then we have the diameter of the pipe, so we'll be using 200 mm. So if we're going to convert that one into meter, so that will be 0.2 meter squared. So we have the value. So we have the value of velocity, which is 1.91 meter per second. So we can completely substitute the value, completely identify the value of the density, water, velocity, diameter, and absolute viscosity. So let's substitute that one here. We have density of water, that will be 998. So the unit of kilogram per cubic meter, and it will be multiplied to the velocity, which is 1.91 meter per second. Then the diameter will be 0.2 meter. Okay. So divided by the absolute dynamic viscosity. So that will be 1 times 10 to the power of -3. So this is Newton. So this is Pascal. So Pascal, so that will be Pascal second. So usually Pascal second, that will be Newton per square meter. So Pascal is a unit of pressure. So I'm going to simplify our equation to break down to celcius para makita nyo yung consolations of units. We have kilograms, so Newton, usually Pascal, no? Plus Pascal, that is equivalent to Newton per square meter. Okay. So I'm going to break down that one. That will be kilogram meter second squared divided by the square meter dun sa ilalim, then this is multiplied by second. So let's cancel the units dito. So we have your kilogram cancel out. So we have your meter. Then we have also meter dito. Square meter. Okay, this is meter. Then we have cubic here. Square meter dito will be cancel out. Okay. So seconds also cancel out. So Reynolds number is a unitless number. So we have now the value of, so I have the value of 380,095. Now this is greater than 4,000. The value of Reynolds number is greater than 4,000. So we can say that the type of flow will be turbulent. So the type of flow will be turbulent. Now we'll be using Moody's diagram to determine the friction factor. Okay. So looking at the Moody's diagram, so I have there, so this is yung value that will be how much that one. So I'm going to express this one in the powers of ano. So this is equivalent to, that will be 3.8 no, times 10 to the power of 5. Okay. So hanapin natin yan dito. So starting from here, 10, this is 1 times 10 to the power of 5. Now meron tayo doon, this is 3.8, so that is 3 and 4. We have this is 3.5, so it is somewhere here. Okay, so I'm gonna write it down here. So this is 3.8 times 10 to the power of 5. Now para makita natin the intersection, so we have here the curvature. Okay, so this is the values for the values of the relative roughness. Now let's solve the value of relative roughness. Okay, so reviewing the problem, so we have here na specify that is wrought iron pipe. So we have wrought iron pipe. So reviewing here from the table, so we have here in table na ito. So we have the type of pipe or surface. We have the roughness. Okay, so that is expressed in feet, and we have here the same factor. So yung makapansin, so we'll concentrate on this one. So we have low, high, and design. Now for steel, mineral, iron, and for miscellaneous. So looking yung kapareho niya, we have type of welded seamless, corroded, riveted, stainless, galvanized, plain, and corrugated. We have concrete, cement, clays, bricks, seaweed. Then for the iron, we have cast plain, cast star, coated, cast cement line, bituminous line, so wrought plain. So we have here wrought iron, so they are almost the same now, so, properties. So we'll be using the design. So for the remaining ano yan, sa tawag dito sa problem natin, so we'll be using the design. So ito lang palagi gamitin at low and high, so we'll be focused on the design. So we have the value of 0.002. Now for the relative roughness, we have the value that is 0.0002, so that is the unit of feet. Now we're going to convert that one, since yung diameter natin, which is in the unit of metric. So we have the conversion that is 1 feet. So it will be 1 meter. So it will be 1 meter. So 1 meter is equivalent to 3.28 foot. So we can cancel the units here and here. Then for the diameter, so that will be 0.2 meter. Okay, so cancel natin yung units dito. So lahat mawawala na. Okay, so then we have, using our calculator, so we have the value of 0.0003. Okay. So plotting this value dito, so that will be 0.003. So mapapansin nyo dito, we have 0.001. This is 2 and this is 4, 6.003. So we can assume nandito siya banda. So we can predict, not assume but predict na nandito banda yung value na yon. Okay, so we have 0.0003 value for that one. Now makikita nyo, we have here the path line going there. So if I want to project this one, so usually tatakbuhan ng line na ito. I'm doing the dotted line. Ganyan dito. Okay. So yan siya. So for the intersection, okay, for the intersection natin dyan, so I'm going to plot the line ito dito. Okay. And so it is somewhere here. Then kung ano intersection niya yan dyan, so for the intersection meet, okay, so that will be the intersection of the Reynolds number and the relative roughness. So we have the corresponding values ng friction factor natin doon sa kabila. So drawing a straight path line here. Okay. So referring to this one, okay, so you will notice dito that is 0.15, no? 0.015 nandito siya sa pagitan ng 0.015 and 0.02. So if you're going to break down yung line natin dito, graduation na yan, that is 5. So we can say this is 6, 7, 8, 9, and then it will be 0.02. So nasa pagitan siya ng 0.016 and 0.017. So let's say, so we can say that the value of your F, or the friction factor dito, is equal to 0.0. So that will be 1. Okay, so 6 and 7, 6.5. So 0.0165. So that will be the value ng friction factor natin dito. Okay, so that is for 200 mm pipe. Substituting, so we have your F, so that 0.0000, then multiply natin siya sa, okay, so tingnan natin here, that is 10 meter. So I'm using that one, that is 10 meter. So 10 meter divided by yung diameter, that would be 0.2 meter. Then multiply natin velocity. So yung nakuha natin velocity, which is 1.91. So 1.91 meter. Okay, so raised to square divided by 2.80 squared. Okay. So using our calculator, so we have the value, your edge 200 mm 5 is 0.0027. Oh, this becomes now 0.0023. So let's round up na natin itong value na ito, 0.003. So ang unit, okay, so let's check the unit, no? So this is cancel. squared and this will be squared. So ito cancel out. So may 1 na lang meter. So we have the unit of meter. So one alternative for F, okay, is using the Highland formula. So Highland formula, so it is equal to 1 over the square root equal to negative 1.8 times the logarithm of the bracket 6.9 divided by the Reynolds number RE plus the relative roughness ratio, okay, divided by, so I'm going to raise this one to 1.1. So let's try to use this one to get the value of the friction factor. Will be the result if they are the same values also. Okay. So usually this formula, so which varies 2%. So 2%. So yung variation niya from the value is 2% varies. Now I'm substituting now the values here. Okay. Logarithm value of 6.9 by the value of our Reynolds number. So referring to our solution previously, so we have 380,095. So we have here 3.5, then plus the ratio of relative roughness, so we have 0.003, okay, 0.0003 divided by 3.7, okay, so that will be raised to 1.11. So using your calculator, so doing the chip solve, so we can get the value for this one. Okay, so I'm sorry about this class, I forgot to use the value here, so I'm gonna change this one. The value of that is 0.165, so we have here 0.0165. sorry about that. Then I'm changing this one, sorry about that. Okay, so we have the result. Unit, so changing that one. So we have the value of 0.16. It is almost the same. Okay, so to ease of computation, so we can so we do not anytime we do not go to plot anymore, so we can use the Highland formula for getting the value of the quite the same. Okay, now let's try to solve the Reynolds number for the 100 mm pipe. So going back to the figure, so the 100 mm pipe runs from the discharge of the pump going to the storage tank here. Okay, so the Reynolds number, we have the density of water, then we have the velocity of the pipe, then we have the diameter inside in the pipe, so this is divided by absolute dynamic viscosity. So meron na tayo, we have the density of water, diameter, we don't have the velocity of the pipe. So take note that we change the diameter, so obviously it will also change the velocity. So volume flow rate, that will be area which is divided by 8. 2 divided by the diameter, d squared. Now the volume flow rate will be 0.06 second. Then we have your pi over 4, then you have your diameter, which is 0.1 in terms of meter now. Yes, we go better, then it is raised to square. So we have the velocity, which is equal to, so we have the velocity which is equal to 7.64 meter per second. So we have the complete data, so we can compute na the Reynolds number. Now the Reynolds number is equal to the density of the water, which is 998, so that will be kilogram per cubic meter. The pipe, which is 7.64 meter per second, then multiply by diameter, the inside diameter, that will be 0.1 meter, and it is divided by the absolute dynamic viscosity to 1.003 times 10 to the power of negative 3. So this will be kilogram meter second squared divided by that is square meter, then this is multiplied by the seconds, so 1.003, so 1.003. Okay, so checking that one, so we're on the right path. So cancel the unit and you have your meter. Okay, so meter here, also this one, cancel out. Okay, then your seconds. So we have now the value of is equal to, we have the value of your Reynolds number, which is equal to 760,191. So this is greater than 4,000, so therefore the flow is, so since it is turbulent, so usually we'll be dealing with the Moody discharge. Now since I introduced the Highland Formula, so yun na lang gagamitin natin from now on. Okay, so we have now the substituting the values here, so we have the square root of f, so that will be negative equal to 1.8 times the logarithm, then we have your 6.9 dito, then divide by Reynolds number, which is 760,191, then plus the relative roughness, so checking that one sa previous solution natin. So the value of the relative roughness now, since we have the same pipe, that is 0.003. Okay, so this is will become 0.0003 divided by 3.7, now raised to 1.1. Okay. So we have now the value of your f is equal to, so we have the value of 0.01, that will be, so round off natin usually, that is 0.01578, so I'm going to round off that into 0.016, okay, for the friction factor. So so this is at 100 mm pipe. So solving the head loss at 100 mm pipe, so we have your HF at 100 mm, so that will be equal to F L over D Then we have the velocity squared over 2 times the gravity. So substituting the value, so we have your F, which is 0.016, then multiplied by the length. So let's check the figure in drawing. Okay. So you will notice here, okay, in the figure, so we have here 5 meters now. So going up, that is 5. Then we have the distance starting from here going here. So that will be 100 meters. So magiging 105 na. Then another distance that is starting from here going up. So that will be correspond to the length of the pipe. So that will be 15. Okay. So we have 15 going up, and we have the horizontal traveling, which is 5 meter going to the storage tank. Okay. So that is a total of 125, the total length of 100 mm pipe. So I'm gonna write down here the 125 meters. Then divided by the diameter, which is 0.1 meter. Then we're gonna multiply it by the velocity. So taking the velocity, so that will be 7.64. So we have 7.64 meter per second. So raise this one to square, divided by 2 times the 9.81 meter per second squared. Okay. So we have now your HF at the 100 mm pipe is equal to, so we have the head loss, which is equal now to 59.5 meters. So let's cancel yung units. So ito, cancel na ito. This one, this one, this one, and this one. So it will be cancelled out. Now, solving for the minor loss, we have your HL, which is equal to K times the velocity squared divided by 2 times the gravity. Yung K natin, so since we have so pinagkaiba lang, referring to the figure here, we have different velocity starting from the suction, since we have different diameter of pipe from the discharge, so 200 mm. So we have 2 velocities here now. So we have 2 corresponding types of head minor losses for this one and for this one. Now let's try to use first to compute the head loss at the suction. Okay, so we have at the suction, that is 200 mm pipe. So referring to the figure, so katulad nga dinidiscuss ko from the last time, so we have the re-entrant, pasok ng tubig dito, then we have your gate valve dito. Now checking this one, so meron tayong, this is almost pareho po. So since we do not have here the value of your L here, and also we have the value of your diameter dito. So re-entrant, okay, so we have the value which is your KL, which is 0.8 for the KL. So that is the pipe inlet re-entrant. So I'm gonna write here the re-entrant dito. So this is HL, which is equal to, so this is 0.8. Then we're going to add the K of the gate valve. So that is GB, so acronym of GB, gate valve. So looking at the figure, nandito yung gate valve nito, which is fully open. Now checking this one, we have bulbs, glow bulb, angle bulb, ball bulb, swing check bulb. So we have the gate bulb here. For fully open, we have the KL of 0.2. So we'll be using this one, 0.2. 0.2. Now, we don't have other fittings maliban na ito, but we're going to disregard this one since it is not shown in the figure doon. So disregarding this one. So this is multiplied by the velocity squared divided by 2 times the gravity. Now the velocity natin dito, so that is on the pipe on the suction, so checking that one. Now for the 200 pipe, so we have the velocity which is 1.91. So substituting that one, we have here 1.91 meter per second. So we raised to square, then divided by 2 times 9.81 meter per second squared for the gravity. So cancel out ang units. We have this one is already being cancelled out. Okay. So we have the units of meter now. So head loss minor, okay, is equal to, so we have the head loss which is equal to 0 point, so I'm going to round off this one to 0.2. So usually that is 0.185 meter. I'm going to round off na lang ito to 0.2 meters. So now for the discharge, so we have the minor head loss which is equal to, checking the figure, so you will notice here we have the gate valve, check valve, then also we have how many elbows, 1, 2, so that is 3, and we have also the discharge line or the exit to the pipe also. Okay, so we have K at the gate valve, then plus yung K ng check valve, plus K ng elbow, tapos we have yung K ng exit. So I'm gonna write here K ng exit, so 5 exits. So here, then multiply it by the velocity squared times 2g. So we have now your head loss is equal to K ng gate valve, so fully open, so it's the same value we're using here. It will be 0.2. Okay. Then plus the K ng check valve, so referring to the table. So mapapansin nyo dito, swing check valve yung KL nya, so that is 2. So we have the value of 2 dito. Then plus K ng elbow, referring here we have the 90 degrees elbow, smooth bend, metered, so mostly ito. So usually we will be using every problem will be using the plunge na lang palagi. So take note of that, and we'll be using palagi plunge. So disregard yung threaded. So I emphasize ko palagi to use plunge type. So we have 0.3. So this is plus 0.3. So take note nga pala, no? Remembering yung quantity nga pala. So we have the quantities of, so this is 0.3, so times yung quantity, so checking the figure. Okay, so we have 1, 2, and we have 3. So we have 3 elbows in total for the dish. So I'm gonna multiply this by 3 now. Okay. So for the pipe exit, checking the figure or figure table, so reentrant pipe exit, so KL is these symbols. So note, base dito, we have the kinetic energy correction factor is 2 for fully developed laminar flow and 1.05 for fully developed turbulent flow. Since we are in a turbulent flow, so we'll be using 1.05. So plus 1.05. Changing this one into a bracket. Then we have the velocity at that point, which is equal to 7.64. So we have 7.64, that will be meter per second. I'm gonna raise this one to square, divided by 2 times 9.81 meter per second squared. So we have the head loss now for I'm gonna name this head loss M minor at 100 mm. So para magkaroon tayo ng distinguish, magkakaiba ng ano nito. I'm gonna change this one to head loss, that we head loss minor at, usually this is 200 mm, which is equal to 0.2 meters. So dito sa kabila we have the value of 12.34. So this is already in meter, so cancel natin to. Now solving for the total dynamic head, so writing the equations, we have TDH. Okay, so we have the change in elevation from point 1 to point 2, then plus the 1/2, no? Velocity 2 squared minus the velocity 1 squared divided by 2 times the gravity, plus the pressure head. So we have the change in pressure from point 1 to point 2, which is divided by the density times the gravity, then plus the head loss at 100 mm pipe plus the head loss at 200 mm pipe, and plus the head loss minor at 200 mm pipe plus the head loss minor at 100 mm pipe. Now for the change in elevation, so referring to the figure, so from here we have the elevation. So this is already the top of the surface, so we can disregard now since we are basing yung reference point natin is at the pump. Okay. So our reference here is already in the pump, so our H1, so this is our call this H1, and this will be our H2. So for H1, so we have your 0, then for H2 we have the elevation, which is 15 plus 5, that will be 20 meters. So substitute natin yung value dito sa total dynamic head. So we have H2, which is 20 meters minus 0. Then we're going to add 1/2 times the velocity at 2. So velocity at 2, so that the velocity at the discharge line. So velocity at the 100 mm pipe. For the velocity of 100, we have 7.64 meter per second. So this will be raised to squared minus the velocity 1, so that will be on the suction. So that will be on the suction, which is the 200 mm pipe, and we have the velocity, which is para doon is 1.91. So we have 1.91, that will be meter per second, raised to square. Now this is divided by 2 times the 9.81, the acceleration due to gravity. Okay. Then plus, so it does not state sa problem what will be the pressure 2 at the pressure 1. So looking at the figure, so wala naman sinabi kung ano yung pressure dito at saka yung sa discharge, and also the problem does not state. So depende na lang yan if that's a problem, the requirement pressure dito at the requirement at the discharge pressure ay dito. Now since walang requirement of pressure for the pressure, the suction and discharge, so we're going to zero that one. So the pressure here, it will be 0 minus 0 divided by density, which is 998 kilogram per cubic meter, times the gravity, which is 9.81. So usually magsi-0 ito. This is one to represent lang. Okay. Then plus we have the head loss at the 100 mm pipe. So we have the head loss, which is 59.5 meters. So add that one, that will be 59.5 meters. Then plus for the 200 mm. So for the 200 mm, we have 0.153. So this is 0.153 meter. Then plus the head loss minor at 200 mm, so that will be 0.2 meters. So ito yun. Okay. Then plus the head loss at the 100, so we have 12.34. So 12.34 meters. So simplifying our equation dito, so we have now the total dynamic head is equal to 20 meters plus value nito as a whole. We have, so I'm going to correct this one. This is already with EG 2G 2 times G, so correcting that one. And this one, I'm going to correct this one. This is already yung 2 nandun na sa labas, so that will be sobrang tayo ng 2. So we have the value of 2.789. So I'm gonna round off this one to 2.8 meters. Then plus, so this is already 0 na ito. Okay. So we plus, we have 59.5 meter plus 0.153 meter plus 0.2 meter plus 12.34. Okay. So finally we have the value for the place it here. We have the value of your total dynamic head is equal to, so we have the value of 94.993. So let's say so this is already meter, so let's say this is, let's round off, that will be 95 meter for the total dynamic head. Now solving for the water horsepower, so our water horsepower is equal to the specific weight times the cooling flow rate times your total dynamic head. Now the specific weight, so since we have the change in value, so it is not 1,000 value na natin ng density, so we need to express the equation in terms of density. So the specific weight, the equation for the specific weight we have, so our specific weight is usually equals to the weight flow rate, no, divided by the volume flow rate. So this is volume flow rate times the total dynamic head. Okay. Then our weight flow rate can be expressed as the mass flow rate times the gravity divided by the volume flow rate. This volume flow rate times the Q. Then we have your total dynamic head. Now we can express this one in terms of densities. That will be density times the gravity, volume flow rate times your total dynamic head. So we can express our water horsepower sa ganitong form. Now substituting yung values, we have your density, which is 998, that will be kilogram cubic meter, then multiply by the gravity, which is 9.81 meter per second squared, then multiply the volume flow rate, which is 0.06, that will be cubic meter per second, then on total dynamic head, which is equal to 95 meters. Now checking the units dito, so cancelling out, so cancel na yung cubic meter natin dito. So we have kilogram meter second square, so that is Newton. Kilogram meter per second square, so this is already Newton. Then we multiply by meters, so that will be joules, Newton meter now divided by second, so it will be in terms of watts. Okay, so we have the water horsepower. Okay, so here we write it dito na lang. So finally we have the value of water horsepower, which is equal to, so we have the value of 55,805. So this is the units of Newton meter seconds. I would say this is already watts. So let's try to convert this one into horsepower. So our water horsepower, so that will be 55,805. So this is already in watts. So we have the conversion that 1 horsepower is 746 watts. Okay. So we have now your water horsepower is equal to, so we have the water horsepower which is equal to 74.8 HP. So usually this is will be round up into a 75 horsepower. Okay, so this is only for the pump lang, no? So this is only for the power of the pump, so iba pa yung electrical. Now given that, let's say, so let's add that the pump efficiency, so the pump efficiency, let's say at the 60% efficient, so we have the equation, your efficiency now is equal to water horsepower divided by your electrical power. So to get the value of your the electrical power, we have electrical power is equal to water horsepower divided your efficiency. So since we have there is 75 HP divided by the efficiency, which is 0.6, so we have the value of the electrical power required to run the water. So we have the equivalent of 125 horsepower for electrical. Now this is for 60% efficiency. Now the 60% efficiency, so this is sometimes called the best efficiency point. So this is the most pinakamagandang efficiency ng pump na required to attain to become more efficient. So that is already in the number of 60%. So palagi yan. So take note of that one. Okay, so looking at the overview of our solution, so we started from here, and the values coming from here and going down. Okay, so medyo mahaba lang ang computation, but it's worth it kung gagamit nito when you do practice in the field. So that's it. So if you have any questions, so please drop by, message mo ako, and if you hindi ko maintindihan. So what I provide here as a step by step, nakikita nyo naman sa solution, so it is a step by step way of solution para maintindihan nyo yung procedure na ginawa ko. Okay, so that's it.